All right, so now that we have a definition for acceleration, we're going to go ahead and try to use it to understand a basic situation. So I've drawn a strobe diagram here for a ball rolling across a table, hitting a wall, and bouncing back across the table. And I've already populated my diagram with position and velocity vectors like you might expect from a motion diagram. And what I want to fill in now are the acceleration vectors to flesh out this diagram using my definition for average acceleration, which says I want to look at the change in velocity and divide it by the change in time. Of course, all the changes in time are the same across the strobe diagram, so I really only have to look at how the change in velocity vector is going as I move from one point to the next. So I can do that for a couple of points here. The velocity is not changing as I move from one point to another here, which means the change in velocity is 0, and the acceleration is therefore 0. And as I move along, I see that I still have a pretty small change in velocity. I go from pretty big to still pretty big. So I'm going to have an acceleration vector here that points backwards, but is probably pretty small. And then I'm going to have an acceleration vector that sort of continues along this way. This one maybe is a little bit bigger. And then it gets back to being a little bit smaller. And then a little bit smaller still. And now I come over here, and I've bounced off the wall. And my acceleration vector looks like it's still pointing to the left, because I want to know, what do I add to the velocity to get the next velocity? Well, I'm going to add to small to get bigger and bigger and bigger. So again, I'll do this up here. Small, bigger, maybe a little bit bigger, back to being a little bit smaller. And then here the velocity is constant again, so the acceleration is going to be 0. And then I can sort of collectively label these as my acceleration vectors at all the different instances. So here we go. I'm going to draw the acceleration versus time. So here I want acceleration. And really what I'm graphing is the horizontal or x component of the acceleration. So I could put a little x there. Here I've got time on my horizontal axis. Again, I've got a position origin up here. And I'm going to go ahead and pick my coordinate to point in the normal direction here, which means that all of these acceleration vectors that I've drawn point in the negative x direction. So as I sketch, I'm going to keep that in mind. And I'm just going to go instant by instant here and try to capture what's happening to the acceleration. So I start out with a 0 acceleration for a little bit. So my graph is going to look something like that. And then eventually I get to a place where the acceleration is increasing, something like this. And then it sort of heads back to being near 0. And then it looks like it goes back to being negative for a while, and then finally gets back to 0 and bottoms out. So this would be my example graph of the acceleration versus time. You could go ahead and draw velocity versus time or position versus time by following along with the arrows that I've drawn up here.